All right, everyone, welcome to this AP Environmental Science lecture on oceanic power. This is only one small part of one learning objective. We're actually in the learning objective for hydroelectricity. However, I'm going to separate all oceanic sources. This learning objective is where they just mentioned tidal energy. We'll talk about tidal. We'll also talk about another couple sources of energy that we can use from the ocean. But I want you guys to think about this a little bit separate from hydroelectricity. When you think hydroelectricity, think a hydroelectric dam. When you think tidal or any of the other oceanic forms of energy, think the ones that we're going to talk about in this PowerPoint. Here's the vocab. You can jot this down if you want to. I'm going to skip it. And let's just jump right into it. So the world is covered primarily by the ocean, and there is a lot of untapped potential of energy in the ocean, whether that is based off of temperature or whether that is based off of movement of water. And like I said, there's a lot of untapped potential. Usually what we're going to do is use kinetic energy of the waves or tides to turn a turbine that is going to generate electricity. It is a very renewable source. The tides are always going to be moving up and down, ebbing and flowing, and waves are always going to be moving as well. There's no way around it, and we're always going to have those energy sources. So they are completely renewable. The different types of oceanic power may be variable, may be consistent depending on the type. Most of them are going to be relatively consistent. However, it can depend on local conditions, including weather and timing. Most of them, if not all of them, are going to be limited to the coastlines. But many of our major cities are coastal, so there's a lot of untapped potential along the developed coastlines all around the world, whether that is New York or London or Beijing or wherever it is. Many cities are coastal or at least somewhat near the coast. However, there is very few installations. It represents a very small part of the world market. There's a lot of R&D going on right now, research and development, but not a lot of installations being built. And the other good thing about this is that there is no emissions associated with their use, so no gaseous waste whatsoever, carbon dioxide or otherwise. All right, so let's talk about the different types. We're going to start with tidal energy, and there's two types of tidal energy. In general, we're going to use the ebb and flow of the tides to run a turbine, but how we do that is where this differs. In a tidal barrage, think of it kind of like a dam. So let's say that we have the coastline, um, and that coastline has like a little bay in it or something like that. And we can create a dam across that and we can fill that up with water during high tide, and then at low tide, release that water back out into the ocean because between the tides, high and low tide, we're going to have high potential energy behind that dam and low potential energy at low tide out of it, and will allow water to rush out through the penstock of the dam during low tide, and we can generate electricity from that. So that's going to be somewhat variable. It's going to only produce electricity when you're allowing water through it, not when you've closed it off and are trapping water behind it. Okay, so at high tide, not much electricity, but during low tide, electricity. The other one is tidal stream. Tidal stream essentially is you just have turbines in the water anywhere along the coastline where the tide is going to rise and fall. And when the tide rises and falls, it's going to bring the current with it. So at high tide, the current is going to flow towards the land, and that water is going to move towards the land and increase sea level. And that turbine can move via that current, like we see on the bottom right. And then at low tide, the current is going to recede and the turbine is just going to move in the opposite direction and still generate electricity as the tide recedes. So both of these just use the kinetic energy of moving water due to the tides to turn a turbine to power a generator to create electricity. There's definitely going to be more habitat destruction or disturbance in a tidal barrage because you have to essentially make a big structure like this rather than sink a bunch of turbines into the ocean as you would for a tidal stream. And then we have wave energy. Wave energy, there's a few types. This is going to use the kinetic energy of waves to turn a turbine, and two of the three types, to power a generator to generate electricity. In the first one, we have an oscillating water column. That is what we see up at the top right, both pictures. On the top left picture, the water is going to, actually, let's start with the top right. At the top right picture, we have the wave coming in. We have the water filling up this reservoir down here while the water is moving in, and that's going to push the air that was in this reservoir. So let me get a different color. All of this air here, it's going to push it up through this turbine, which will spin due to the power of moving air and and generate electricity, because it's hooked to a generator. If we look at that, once that wave recedes, so the wave comes up, pushes air up into that turbine, spins it, makes electricity. Once the air recedes or the water recedes, we have that wave going back out, and it's going to suck air in from the outside, spin the turbine, power the generator, and every single wave that moves in and then out, compresses and moves that air through the turbine in one direction or sucks it out, sucks it in the other direction. So we can provide very consistent energy as long as there's wave action. And there will definitely be more energy the stronger the waves, less energy the weaker the waves. Overtopping devices are essentially things that are floating in the ocean, and the wave will rise up, crash over the structure, fill up a reservoir that is in here, and that reservoir is higher than the surface of the ocean down below it, and it will therefore want to, via gravity, flow into the rest of the ocean water and do so past a turbine, which is hooked to a generator, which can generate electricity. So that is an overtopping device. And then finally, an oscillating body. An oscillating body is the one that is not going to be using a turbine. Instead, it's going to have this buoy that is attached to this line that is holding this kind of like you can like this spring body thing. And as the wave, as the buoy goes up and then down via the waves, it's going to move this spring up and down, and that associated with all of the complicated machinery in here that's a little bit beyond this class, way beyond this class, is going to generate electricity. So it's going to not use a turbine. It's like the only thing, one of the only things that we're going to talk about in this class that doesn't use a turbine to create electricity. And then finally, a ocean thermal energy converter, or OTEC. This is a device that uses the temperature differences of water to vaporize and then condense a fluid that travels through these pipes. And as it does so, it's going to go past a turbine, spin a generator, and generate electricity. So let's talk about how it works. Typically, it's going to be using ammonia or propane, something with a really low boiling point. You guys probably know that ammonia is a liquid at room temperature, but it easily vaporizes. You can smell it really easily. And if you heat it up just a little bit, it's going to boil. Or propane is a gas at room temperature, so it has a very low boiling point as well. You're going to have warm surface water up at the ocean surface, up at the top of the ocean, that vaporizes this. That'd be in this purple section of pipe right here. So we have vaporized ammonia or propane or whatever other gas they're talking about going this direction past a turbine, which is powering a generator, which is making the electricity. And then it's going to go down into back into the ocean to a condenser. And this condenser is going to use cold water from the ocean to cool it, like the deep water from the ocean to cool it. And it's going to turn it back into a fluid where it will rise, be warmed up by the warm water at the surface with this heat exchanger right here, and it's going to evaporate and complete the cycle again and again. And because it evaporates in these pipes, it's going to be at high pressure, and that's what's going to cause it to go past the turbine really, really fast. Okay, so essentially what you're doing is boiling and then condensing a fluid, and as it boils, it expands, turns to a vapor, and has a high pressure, goes past the turbine really quickly to generate electricity. Then you're using cold water from the deep ocean to cool it, condense it, and then warm water from the surface of the ocean to bring it back up. And notice the temperature difference. Negative, 5 degrees Celsius way down at the ocean depths versus 25 degrees Celsius up at the ocean surface. That is definitely warm enough to boil propane or ammonia. You mix the two of them so you don't release cold water at the ocean surface and shock organisms, or release hot water at depth and shock organisms that way. So we have these different types of ocean power, but they only represent 0.001% of the global economy, or at least they did for this graphic that I found from 2010. Very small portion of the world economy, but definitely a growing portion and huge potential to expand, especially again because many of our population centers are coastal areas. In terms of what we have today, the overwhelming majority of oceanic energy is tidal barrages. You notice that it's only in the megawatt range, not even the gigawatt, much less the terawatt range. We're talking about megawatts worldwide. So very little electricity production, but the majority of it is tidal barrages and then tidal stream, wave energy, and then we didn't even talk about salinity gradient, but it's pretty cool as well. You can look it up. But again, huge capacity for expansion. And then just showing this data on a different way. So oceanic energy capacity per year for different countries. And you notice that, kind of ebbs and flows just like the tides does, um, although it is rapidly increasing in the past few years. The largest inhibitors to installation are a global focus on wind and solar as the only renewable energy sources, but we need all energy sources specifically apportioned or used in the places where they are most like logical to do so to get off of fossil fuels, right? We can't just focus on wind and solar. Wind and solar has to be a big piece of the puzzle, but there are other pieces of this puzzle as well, including oceanic power that we should be investing in. It does have some high upfront cost. It is difficult to install many of these things out in the ocean. They do produce very little power individually, but together, like large arrays of them can produce a lot of power. And salt water definitely is corrosive, so there's definitely maintenance costs, especially with any metals that you use in these that are in contact with salt water. So where is the greatest potential for oceanic energy resources, especially tidal? Again, we're looking at our coastal areas. The tides are not the same everywhere. Some places have tides that are relatively minor in change of sea level. Some places is very drastic change in sea level, like 10, 20 meters even in terms of change in sea level. Some places the tide is going to come into like a rocky bay that has like a cliff drop off. Other places it's going to rise up very slowly along a really large mud bank. And that difference in topography is also going to affect whether or not tidal or oceanic power in general is applicable in that area. But I will say that this is just focusing on tidal resources. Wave energy is applicable pretty much any coastal area as well as OTEC energy because there's always going to be a difference um, in surface versus deep water, although it's definitely going to be most applicable in the warmer temperate or tropical regions or subtropics and tropical regions than it would be up in the Arctic regions where it's going to be less of a difference between very cold surface water and very, very cold deep water. Some of the negative effects of these, tidal barrages can have many of the same negative impacts as traditional dams because you are essentially creating a dam. There's going to be habitat disturbance, there's going to be habitat destruction, there's going to be impounding of sediments on the other side of that dam. There's going to be adverse impacts to the habitat. There is potential for marine organisms to get caught in machinery, especially propellers, sorry, not propellers, but turbines, turbine blades, or power lines, especially in tidal stream or some of the wave energy. There's underwater noise that can interfere with animals' ability to echolocate if they are cetaceans or otherwise use any type of auditory cue. Electromagnetic fields around the cables and wires can affect the feeding and orientation of many marine species, but we see the same thing with offshore wind because we need cables moving at the bottom of the ocean floor for those as well. And we can have changes in local ocean circulation, especially with tidal barrages, because they're impacting the way that the tides are working. You can also have this changes in sediment movements, again, especially for tidal barrages, because those are the only ones that are affecting or impounding sediment. I will say also, though, that some of these can act as habitat for some sedentary marine organisms. So Yeah, actually, that's on the next slide, so we'll get to it. So, like I said, some of these can provide habitat for sedentary or sessile marine organisms. So, clams and mollusks can use them as habitat, just like how they use the bases um, of offshore wind turbines as habitat. There is no greenhouse gas emissions from their operation, so that is definitely a positive impact. That is the biggest draw to use them as a transition off of fossil fuels, right? They're completely renewable. Even if it's a variable energy source, you can definitely figure that out with the local grid and adjust everything in the grid to meet that, whether that's having battery backups or whether it's turning on a nuclear power plant a little bit higher during that time or whatever. Most of them, though, are going to be consistent energy sources, especially the ones that rely on wave energy. Again, many cities are coastal, so it has a huge potential for expansion, and many of those coastal cities already have heavily impacted shorelines. So the effect of adding just a series of tidal stream or wave energy or even tidal barrage power plants is not going to be that much in terms of habitat destruction because the habitat's already destroyed, So I hate to say it that way, but it's like how in Colorado the Gold Key mine had like dam failure had very little negative environmental impact because the rivers were already so heavily polluted. It's the same thing here. If you add a tidal barrage to a coastal city that is all just nothing but concrete along its coastline anyway, then there's not much habitat to destroy. So why not just go ahead and create a tidal barrage there? Anyway, I hope you guys learned something definitely beyond the learning objective, but you should know this stuff anyway. I'm going to use it on my quizzes and tests. You may see it on AP, and you should be able to argue it on an FRQ anyway. So yeah, definitely beyond the learning objective, but hope you learned something. I'll see you all in class. Bye.